The charging speed in terms of time is a combination of the charger power and the size of your battery as well. There are some physical limits in terms of how fast I think you can go. So as you go above 250 kilowatts, you start to enter into a realm where the power and the current that you're passing through the cables becomes so much that you start to need some liquid cooling. Those liquid cooled cables are, one, more expensive, and also two, they start to become unwieldy from a normal consumer. So you would expect the limitation is, can a normal consumer with one hand pick up a charging cable and plug it into their vehicle? Now, if you've got a huge copper wire with cooling around that, that's going to be a limitation as well.
Welcome back to Battery Generation, your e-mobility podcast for European battery research. Leonard, good to see you back.
Good to see you too, Patrick. And we are talking to an outstanding guest today, Dr. Billy Wu. Welcome to Battery Generation.
Great, thank you for having me.
You are an associate professor at the Imperial College in London and director of research in the Dyson School of Engineering. You co-lead the group Electrochemical Science and Engineering, and you are on the editorial board of Energy and AI.
Dr. Wu, we are going to talk about charging of batteries and battery digital twins. Let's start with the charging part here. And in order to get our listeners started over there, of course, everyone knows by charging an own phone, there is normal charging and fast charging. What's the basic difference about these two charging approaches?
The main difference between fast and normal charging is down to speed. If we take an electric vehicle, for instance, compared to an internal combustion engine vehicle, you might refuel in maybe 4 or 5 minutes and be on your way. But first generation electric vehicles, if you were charging at home, would take maybe 8 hours or more, depending on how you charge it and so on. So from a consumer experience perspective, there's a huge gap between existing technologies and new technologies which we need to bridge. So going faster by putting more power and current into the system helps us to get closer to conventional technologies for electric vehicles compared to internal combustion. But obviously there's drawbacks with that which we need to manage and so on. And the same principle applies in mobile phones and laptops where you might use your device and you forget to charge it and then you need to run out the door. So the ability to charge it rapidly would be very advantageous from a consumer perspective.
What's the hold on? What does it depend on how fast I can charge?
The answer to that is partly how long is a piece of string to a certain extent, in that we can go faster, but there's a trade-off. So within batteries, we often talk about the and problem, where it's easy to make a battery with high energy density, it's easy to make a battery fast charging, it's easy to make a cheap battery, but it's hard to make a battery with all of those characteristics in the same device. So in that sense, what's holding us up is the combination of those parameters. So you want to fast charge, but equally, you want to make sure that your battery, one, doesn't explode and catch fire. That's probably the most critical parameter.
Yeah, I do not want that.
Yeah, most people would like their phones and electric vehicles not to catch on fire. So I would say that's the first criteria to make sure that your battery doesn't have safety risks. The next thing is the lifetime of the device, which is a scale in terms of how much degradation you cause from the fast charging. So I would say those are the things that kind of are holding us back. One, is it safe to charge your device rapidly? And two, even if it is safe, what damage is it causing to the asset? And at what point do you say, I can accept the degradation that I cause from that device? And those are the questions that developers and engineers are trying to grapple with alongside consumer expectations, where people are expecting their devices to last longer, but also charge faster.
These developers of batteries in general, they develop charging algorithms, charging profiles for every battery they develop or produce. Could you once more explain this concept of CCCV, constant current, constant voltage? I guess CCCV is applied to most of the existing batteries out there, correct?
Yeah, you're completely right. So whilst there are lots of different ways to charge the battery, the most standard way is the CCCV profile, which, as you say, stands for constant current and constant voltage. What that means is that when we first plug in our device, assuming it's fully dead, so 0% state of charge, is that I apply a constant current into that device and it slowly increases. Now, once you get up to a certain level where the battery's almost full, we enter into what we call the CV phase, or constant voltage. That's where the current starts to decrease. And normally, when people quote the time it takes to charge their device, they might say a time up to 80%. And the key gist of it is that the last 20% or so often is quite difficult to get into the device. So you've got to be a little bit careful with how people quote these charging numbers, where people often say it only takes me half an hour to charge up to 80%, because that remaining 20%, even though it's useful, can be very slow to put in.
So you're saying for that last part, those last 20%, you're trying to keep the voltage at the same level, which means probably that you're not keeping the current at the same level anymore, right?
Exactly. So going back to the main criteria for battery safety is for it to not explode. If you overcharge the battery, and we interpret overcharging in one way by taking the voltage too high. So most batteries operate between 4.2 and 2.7 volts. If you keep applying that same current up to 100% state of charge, then what will happen is that you overcharge the battery. Some of the materials in the battery can decompose and they produce gas. So if you ever see your own mobile phone or laptops swelling, that's an indication that bad things are happening. And we want to avoid that. And that's why that last 20% is quite difficult, because to avoid gas being generated and safety concerns, we need to slow down the charging, keep the voltage within safe limits.
I've actually seen that swelling part at an old phone, right? Something that has been in my drawer for almost 10 years, like I think it was an old iPod, and then it started to swell, and I thought, okay, this is probably the moment to recycle it.
Yeah, and definitely get rid of it very quickly, because at that stage it can be, although it's not conclusive. So within the safety field, there's loads of uncertainty around, how to predict safety, how to mitigate it. But certainly a swollen battery is something that I would certainly be very concerned about. So getting rid of it as soon as possible, even though it might still charge and discharge, I would highly recommend people get rid of it.
Now, CCCV is not the only charging profile that exists out there. I have read something about boost charging, then constant power, constant voltage, or even pulse charging. Could you explain what's with all these different charging profiles?
So one of the things that we're trying to do is fast charge the battery, so push as much current into the battery as possible without damaging the battery and maintaining its lifetime. One of the main ways that batteries degrade and also fail is something called lithium plating, or formation of lithium dendrites. What this does is that it effectively short circuits your battery, so basically allows loads of current to flow very quickly, and that causes the battery to heat and ultimately explode. So the aim of a lot of these battery fast charging algorithms is to prevent lithium plating from occurring. An analogy that I like to use is that you can think of a battery as having two bookshelves, right? So you have your anode, which is your negative half, your cathode, which is the positive half, and they're both bookshelves. When you charge and discharge your battery, you're moving lithium ions or books from one bookshelf to another. So say, for example, you're charging your battery, your anode bookshelf is completely empty, and I'm putting books in. It's very easy for me to slot them in because there's lots of space for me to do that. However, as I fill up those bookshelves, the space for me to put in new books becomes more and more difficult to find. And if I try and push books in at too high a rate, then that's analogous to basically me causing lithium plating. So the books don't fit into the bookshelves, they spill over, and that's basically what's happening inside of a battery, if that analogy helps.
So now I imagine that in every EV there's a different type of battery, and we also have a variety of battery chargers. So when I pull up with an EV to a charging station, who will decide what of these charging algorithms is actually used? Is that the battery or the battery management system, or is it the charger that decides it, or how is that even worked out?
So ultimately, there are so many different types of batteries out there. There are some energy dense batteries which give you range. Normally, there's a trade-off between energy and power. So the more energy dense your system, the lower the power and the harder it is to fast charge. If you get a more powerful battery, so the Porsche Taycan is often quoted as one of the faster charging electric vehicles on the market. The challenge there is that you sacrifice energy density, so it doesn't give you as much range in that case. In addition, we've got different chemistries, so lithium iron phosphate, NMC chemistries, and others out there. So, one, there's a diversity of chemistries. Chargers themselves, which companies provide, they are often rated to a certain power, so 250, 350 kilowatts. And that's the rated power that they can achieve at maximum. And you should be careful that actually some of the time you can't achieve that full power. So going back to your question, often it's the battery management system that dictates how fast you can charge. So even if you pull up to a charger that can do 350 kilowatts, your vehicle might not necessarily allow you, and that might be dependent on the age of the vehicle, the temperature of the battery. So fast charging at low temperatures can be very detrimental. And I suspect the battery management system wouldn't allow you to damage the battery. Now, each company does their fast charging in a slightly different way, and there is an opacity there. But normally, it's the battery and the vehicle telling the charger how much power to give it. That can lead to some consumers having a poor experience where they think, oh, my vehicle says that I can achieve this, and I pulled up to this charger that says I can do this, but I'm actually charging much slower. So there is this expectation management that people need to do as well in terms of making sure people understand the technology. But ideally, we design batteries which can do all of these things, but we're not quite there yet.
Let's stick to an example. The Porsche Taycan that you just mentioned, I think is offering 270 kilowatts. In Germany, at least, there is HPC high performance chargers that offer a lot more. What do you think? How fast may we charge our electric vehicles in the future?
I think a lot of fast chargers right now and vehicles, they can charge, 20 minutes, 30 minutes. That's what you can see now. Obviously, if you can get it much lower, that's ideal. Now, the charging speed in terms of time is a combination of the charger power and the size of your battery as well. There are some physical limits in terms of how fast I think you can go. So as you go above 250 kilowatts, you start to enter into a realm where the power and the current that you're passing through the cables becomes so much that you start to need some liquid cooling. Those liquid cooled cables are, one, more expensive, and also two, they start to become unwieldy from a normal consumer. So you would expect the limitation is, can a normal consumer with one hand pick up a charging cable and plug it into their vehicle? Now, if you've got a huge copper wire with cooling around that, that's going to be a limitation as well. So I think there's a few trends to kind of keep an eye out for. Are battery sizes going to be smaller? If so, then basically for the same power, you can charge much faster. And two, are the batteries themselves going to be designed in such a way to accept fast charging? So I can certainly see, and within the research domain, people have talked about extreme fast charging where you can achieve 10 minutes or so. And I think that is achievable right now. But in terms of practical deployment, you also need to think about all of these other factors, such as battery size, the charging power, whether you need liquid cooling on the cables or not. So those are some of the considerations that I would highlight.
I think you're referring to extreme fast charging, for example, by the company StoreDot. They offer a silicon anode within lithium-ion batteries, and now you're also talking about these high performance rates. I ask myself, in terms of thermal management, if we want to hypercharge our electric vehicles in the future, how important is thermal management to these batteries that need to be cooled, definitely, when you want to charge your battery in fewer than 15 minutes, for example?
In addition to not overcharging your battery, which the indicator is the voltage, if it goes too high, that's bad. We also need to think about the temperature, so thermal management. So most lithium-ion batteries don't really like to operate above 60 or 70 degrees. If you go above those temperatures, you start running the risk of entering into what we call thermal runaway, where the battery heats up, it generates its own heat internally, and then catastrophic things happen where you get fires and explosions. So often the speed of your fast charging is defined by which is the limiting factor. Is it the voltage? Is it the temperature? And then once you solve one, you gradually go down. So of course, we can firmly manage our batteries, remove the heat, and then you hit a different bottleneck. And what scientists and engineers are doing is that they're constantly trying to play this battle of, I've solved this problem, let's move on to this. Oh, I've solved this problem, now this has become a problem again. So you definitely need thermal management, because as you push that amount of current through the system, you are going to generate more heat in the system.
Research is focusing a lot, as you mentioned, on mathematical models lately to effectively carry out battery charging. What is your approach here?
One of the most common ways of improving battery fast charging speed, you alluded to it earlier, was what we call anode potential control. So if we can understand at what point we start causing lithium plating and then just keep it below that, that's one of the theoretical limits that we want to push the batteries up to. And your second point is that these limits in terms of when I can fast charge and when I can't fast charge are dependent on the environmental condition. So if it's really cold on that day, I probably can't fast charge as much. But equally, as my battery ages, then I should actually change the way we operate. Just like you and I, as we age, certain physical metrics change as well. If you've broken your leg, you probably shouldn't run a marathon. And it's the same sort of premise that you want to apply to batteries, that as they age, essentially, what should I do to change the fast charging to make sure that it charges fast, but also doesn't damage the battery?
Now, you already answered a question from our listener, Felix S. Thank you very much for sending in this question for Dr. Wu, Felix. Do charging stations actually take into consideration how much my vehicle's battery is degraded? I would love to reduce the speed if harm was done.
Obviously, there are lots of different vehicles out there. Some suggest that they do, where you might have what we call adaptive fast charging. So the adaptive element comes from measurement of the temperature, measurement of the age of the battery, and changing how you fast charge it. I wouldn't say everyone does that. So it is quite mixed in the field right now. It's quite exciting because there are no new solutions coming out there. Some mobile phones and laptops also offer certain fast charging solutions as well. And this is a slight digression, but I think, of course, fast charging is important, but there's also smart charging as well, where it's quite detrimental to keep your devices fully charged over time. So with your mobile phone, your habit is that you go to sleep, you plug in your device, and it fully charges. And it might be fully charged by 2 a.m., but you only wake up at 7 a.m., which means that actually you're causing additional degradation by keeping your devices fully charged over time. When we say smart charging, what we're trying to do is say, the system has learnt, or you tell it when you wake up or when you need your asset, and then it might charge up your device to about 80%, keep it there, and just before you need it, top it up. What you're doing then is you still get the same functionality. However, you minimize the degradation.
Let's now switch to the topic of battery digital twins here. As a researcher, you're developing these battery twin models. First of all, what is the purpose of these battery twin models?
So a battery digital twin is a real-time representation of a physical asset. So we use these digital twins to make asset-specific optimal decisions. And what does that mean? So if we take, for example, the example of those sharing e-bikes that exist in many cities right now. So I can hire an e-bike. Each one of those e-bikes is being aged, it's being used differently, it's out in environmental conditions. And I suspect from new to 1 year, 2 year, 3 years down the line, they all behave very differently. Naturally, when you go up to one of these e-bikes, you check its charge, and maybe you pick a bike, maybe you don't. So the digital twin, basically, if it was to be implemented, describes what that battery health is. It might advise the company, which is a fleet operator, to kind of distribute their assets in different ways. And it all goes back to, we are going to a future which is going to be battery powered. Can we be more intelligent with those assets? So if you're a large fleet operator, say, for example, Amazon, who owns many thousands of delivery vans, which hopefully will be electric, can they schedule the charging intelligently? Can they distribute their assets in the right situation to maximize the value of their fleet?
So it's not only targeted towards designing of new batteries, but also using the batteries better. I think that's how Professor Howie mentioned this in the previous podcast. But once more, what are like the other reasons of developing these battery twin models?
Let's have a look at traditionally how we've done battery control, which might have used models, for example. And a digital twin is a model to a certain extent, but it represents the current state of that battery right now. So if I just have a model that I have developed, the parameters which go into that model would be the same for everything. But we know from changes in how we use the device, in the temperature, in all of these other conditions, that over time these parameters change. I suppose an analogy might be if you've got twins, you've got this nature versus nurture argument where genetically they might be very similar at the beginning, but over time, as they age, they will become very different depending on their lifestyles and so on. And naturally, as they mature, they might be very different by maturity, and the same principle applies to batteries. Where that is relevant is that if you have a battery which is entering it to its end of life, so 80% state of health is often what we quote for the end of life for a automotive vehicle, then the question that you're asked is, should I use this for a second life application, such as stationary grid balancing? Should it be recycled? Or a whole raft of other questions. If you have that up-to-date understanding of that asset, it allows you to be more efficient with that decision making.
So you're saying you're developing a digital twin for every single battery itself. It's not a model for a type of battery that came off a production line, but actually for every single one, there's some sort of database where this is represented. How precise can these models be? And do you need some sort of feedback loop? I would imagine that I would need some sort of sensory inside the battery that will reinform the digital twin in regard to this aging process that you mentioned, right? So how's that actually? How does that work?
So obviously, to update the parameters for our model, we need to be able to measure in real time or near real time those parameters. So you're completely right that we need to measure the voltage, the temperature, the state of the batteries. These digital twins are used in lots of other fields. It's not just batteries. So in the aerospace industry, you've got large assets like planes and engines. And the question you're trying to answer is to maximize the usage of that vehicle, which is really important in terms of profitability. How often and when should I bring it into a service? Traditionally, you might have said, okay, I'll do that every 4 years, but obviously, if you've been operating it through harsh conditions, you might want to do that more frequently. In the UK, we have a servicing schedule, the MOT, which is done at certain periods of life. Is that the most optimal? Probably not, right? So it's basically using the sensor data and saying, when should I change the usage of my device? When should I service it? It's those sorts of intelligent decisions that are starting to be unlocked. And with a lot of new legislation coming in around battery passports, and also the resale of vehicles is a big market as well. So in the UK, obviously you can buy a new electric vehicle, but the cost is quite high. Second-hand markets are often quite popular. But the question then becomes, how do I value my electric vehicle? It's often very different to how you would do the valuation for a traditional internal combustion engine vehicle, where it might be purely based on mileage or age. Here, if you've been constantly fast charging, if you've been leaving it in very hot conditions, that's very different to another vehicle which hasn't done that. So slow charging all the time in very moderate climates, and you might be at similar sorts of state of health. So it's those sorts of questions we're trying to answer with the digital twin.
So would I have access to my digital twin when I resell an electric vehicle in 10 years or so?
The aspiration might be that consumers have access to this information. However, having talked and worked with people in this field, I think we need to strike the balance between accuracy and simplicity as well, because already with range numbers, you want to quote a range so that consumers understand the capability of the vehicle. Now, many people in the field know that that range number can vary considerably depending on the load profile, the type of driving, the conditions as well. And similarly, battery age can be very complex. I don't think the end solution is to provide this model for consumers and for them to look through all the individual lines of code. but they probably do want to understand state of health and what that actually means. We also need to challenge the metrics that we're using, where state of health, whilst it is useful, is not actually the perfect metric, because not only do you care about the current health of the battery, you also care about its future lifetime, or what we call the remaining useful lifetime. So you might have two batteries which are at 90% state of health. One battery, because of how it's being used, could degrade significantly or reach what we call its knee point in another 100 cycles, whereas the other one might have 500 cycles before it's degraded. So therefore, those two batteries at 90% state of health should not have the same value. But right now, consumers only see that singular value. I think that's something for future developers to kind of think about. What is the most appropriate metric for us to use and therefore value our assets in terms of their depreciation?
So this is going to be a very fascinating field. To sum it up, there's in the digital twin, there's all this information stored, and it's basically a literal digital representation of what's going on in that very specific battery. But that information is so complex that it's not directly useful to non-scientific, non-engineering personnel like myself. So there would be something, maybe even the EU battery passport would come in handy there or something. I would need some sort of simpler metrics that will allow me to evaluate the worth of that battery.
I think we start to enter into a regime as well where data is really, really valuable. If you collect loads of data, it's great to a certain extent, but there is a burden there that if you collect terabytes worth of data, there is a finite cost to that. So we need to be smarter about how we collect the data and also what we say as data privacy as well. So say, for example, smart meters are very common in the UK. That collects data around how you use energy. However, if someone had access to that data, they can tell when you're at home, what appliances you use. So there's lots of information in there that maybe other people might not want to share. So if I've got your battery data, I know when you go to work, which could be quite revealing, when you go to sleep, and so on. So we also need to respect people's privacy as we develop these systems, that it gives you the sufficient insight that you need to value your asset, which might be important if you want to sell the vehicle. But it doesn't necessarily reveal too much about your own usage profile, which you might not be comfortable with.
Dr. Wu, you haven't really answered the question of how precise these battery twin models are as of right now and how precise these predictions are already.
So in terms of accuracy, to give you a qualitative answer, I would say they're very good at predicting right now how much remaining range you have to a certain degree, right? I would say it's in the single percentage errors. So for a consumer, you wouldn't really notice the difference. Where it starts to get a little bit tricky in terms of accuracy is when you start forecasting into the future. Now, just like with weather, if I look at the weather forecast, I would be pretty confident of today's weather forecast. As I look a few days into the future, I'm less certain, and in a month or so, I might have some indication of that, but I wouldn't trust the weather in a month's time. And similarly with batteries, I think we've got a very good certainty in terms of what the current lifetime of the battery is, what that would be in a month or two's time. But as we look into the future, that uncertainty increases significantly. And there needs to be a shift in terms of how people look at batteries, that people often forecast lifetime and give you a single number. So your battery will last 2 years more. But actually, you need a probabilistic view on this, which is basically, I think it will last 2 years, and this is my confidence interval in that time. This is really important for people who develop, say, for example, insurance premiums, where you can never be sure that with 100% certainty that this event will or won't happen. So you need to understand the probability that that occurs. So I would say that's kind of where we are right now. Very accurate in terms of describing the current state of the battery. As we forecast into the future, short term, pretty good. Long term, it's kind of a finger in the air at that stage.
Dr. Wu, last summer you have published a paper with Mathieu Dubarry and David Howie on battery twin models. And inside that paper you state, with a combined effort across the battery supply chain, battery digital twins have the potential to significantly accelerate the pace of development and improve the understanding of root causes of failure while reducing cost and enhancing battery lifetime. I mean, that sounds too good to be true, honestly. How do you mean that exactly?
If we take a step back and look at the battery industry, there are multiple players. You've got miners, you've got material providers, cell manufacturers, vehicle operators, recyclers, and so on. So you have cell manufacturers like Panasonic, who provide cells to vehicle integrators who might make them into battery packs. And there is often an opacity in terms of information sharing, in terms of when we buy in lithium ion battery cells to test. We sometimes don't know the exact composition of the electrolyte, which impacts its lifetime and so on. That's obviously known to some people. And equally, the cell manufacturers might not know exactly how the fast charging algorithm works because there's intellectual property at each stage. So that statement that you kind of alluded to, we think that there's a lot of benefit in terms of sharing insights across these different disciplines. But at the same time, you need to respect people's intellectual property. So we see this digital twin as being a vehicle for information sharing, which tells you what you need in terms of the key information about how is the battery going to degrade or respond to the stimuli without telling you too much about, do I necessarily need to know the exact composition of the material? No. But building up that database so that manufacturers who might be trying different things out with additives know 5-year, 10-year down the line in real world conditions, how their vehicle performs, that can be really useful for that closing that loop. And again, it's all because there's this disconnect in information across that supply chain, which is slowing down the rate of innovation, in our opinion.
So there is never going to be like an exact digital twin of a battery in terms of maybe right down to the atom. But you're saying the focus is on the battery's performance factors, right? So if you want to collect this information, you obviously would need some sort of standard or interface or protocol where you gather that information. Who is going to run the simulation? I mean, that takes money, that takes computational power. And you need to talk to all these people. Someone's going to pay for this.
My take on where we are right now is that this holistic digital twin approach doesn't exist right now because of fragmentation within the industry. It certainly can be done from a technical perspective. And what people are doing right now is that they operate within their domains. So I think people are starting to apply these digital twin principles to operation of the vehicle, where you might have a battery management system developer who can basically buy in cells, measure the state, and they've got access to that data. And to your question, I think the types of models you use and the data fusion techniques or the algorithms you use are limited by what's available to you. So you would basically use algorithms which only are based on not knowing what's inside of the cell, and there are a whole range of diagnostic techniques. Obviously, if you have a partnership with a cell manufacturer, you can implant internal sensors that changes what you can do. But the direction of travel for the industry, in my opinion, is dictated by what's available to you. We adapt based on that.
Do I need new types of sensors to keep this digital twin running? Or can we do it with the current set of sensors, and we just need a lot of modeling and algorithm part to have something precise?
My take is that you can achieve maybe 80% of the outcome with the existing technology right now, where I would say the vast majority of batteries, if not all, will measure voltage, temperature, and current to varying levels of accuracy. There are a whole range of other new types of sensors coming out, including strain sensors, pressure sensors, ultrasonic sensors. And these will add costs. They provide different pieces of information. And it all goes down to, where you sit in terms of the cost of the system. So you might imagine a stationary grid system, which naturally might want to run for slightly longer than an electric vehicle or a mobile phone. You might assume in that case, the value of adding additional sensors is worth the cost because you want that extra lifetime in that case. So it's very much case by case basis. And the more data you have, the better the accuracy. Going back to the human example, obviously you can do very simple approximations of your own digital twin of, I can stand on a scale and measure my weight. I can measure my height with a tape. But getting things like my blood pressure and other types of physical metric, they become increasingly difficult. But we've already seen in some fields like the insurance industry, where apparently now some insurance companies, they offer discounts on your health premium if you do a certain number of steps, and therefore they're monitoring your own usage in terms of do you take the number of steps from your Fitbit or other smart device. So I think it's really exciting in the future in terms of the broader market, in terms of how data is influencing how we operate.
Of course, this approach of a battery twin model, the critique about this sounds like this is an academic model, like just like the world model. It'll probably never exist. If you turn this around and take a look at the Chinese battery cell manufacturers, it's actually quite integrated. They own mines, they do the cell production, they do the battery production, and now they're producing the vehicles itself. So actually, there's no question whether these battery twin models are very, very necessary for these big companies that do everything by their own, I guess.
Yeah, I completely agree. I think my take is that as you become more integrated, you unlock these capabilities to do that. Obviously, in companies where they don't have the scale to do that, it might be a bit more challenging and you might have to innovate in different ways. My opinion is that we are seeing so many changes in technologies that actually there is sufficient room for these companies right now, and the market hasn't reached saturation. But certainly with these companies that you mentioned, like CATL, BYD, where they've got very vertically integrated from mine almost to vehicle, there is that opportunity to unlock these capabilities and be smarter. And also work with people outside of that ecosystem, where we shouldn't forget electric vehicles isn't just about developing better batteries. There's also the financing of these, where banks need to understand depreciation rates. There's insurers who need to understand risk profiles as well. And in the future, companies like Tesla are offering insurance products, but not everyone is right now. And we also need to think about those users as well, and what tools we can develop as a community to address the broader business needs as new business models come out.
Dr. Billy Wu, thank you so much for this talk. That's it for today. Billy Wu, all the best. Bye-bye.